Hi everyone, my name's Susan Orgel and I'm a soil carbon researcher with New South Wales Department of Primary Industries. I'd like to start this presentation by talking about the flows of carbon around the landscape. Plants, through the process of photosynthesis, use carbon dioxide from the atmosphere, energy from the sun, and water to grow. Now, through this plant growth, we have carbon going from a gas in the atmosphere to a liquid within the plant into the structural elements of the plant as well. Now, carbon can be accumulated above ground in the form of leaves and litter or manure if we've got grazing livestock in these paddocks, and also below ground in the form of roots and root exudates. Approximately 60% of all carbon which is captured through this process actually goes below ground into the soil. Root exudates account for about 50% of those below ground root accumulations. Now, this carbon is carbohydrate-rich substances which leak out of the plant roots. The reason that plants do this is to encourage microbes to come and live within the root rhizosphere, because microbes help plants access nutrients, moisture, can regulate changes in soil pH and soil temperature. Now, collectively, once organic matter is in the soil through this process, we refer to it as soil organic matter. Soil organic matter can be protected. When I say protected, it's from loss via erosion or degradation via microbial processes and decomposition. Now, it can be protected within aggregates or soil structure, crumbs of soil which wrap up organic matter and protect that organic matter from further loss. Now, that crumb of soil or that aggregate could be located within the soil profile, further enhancing its protective capacity. Organic matter is also a really important source of energy for microbes, and microbes can transform organic matter into more stable compounds such as humus. Different types of organic matter, and humus in particular, can become chemically protected through its form in the soil and also by associations with clay minerals in the form of organomineral associations. Now, I've been talking about organic matter, but we can break this down into different fractions of soil carbon. And the three fractions that we often speak about are humus, which is the majority of that soil organic carbon pool. Now, humus is microbial products and microbial detritus. There's particulate organic carbon, which is the energy-rich substance, which is like the kind of cash carbon flow, which provides energy for microbes. It can be very management sensitive, so it can build up quickly, but also can be lost rapidly as well. And then we've also got charcoal, or very fine bits of char within the soil. In our Australian soils, charcoal can account for up to 35% of this total organic carbon pool. But as I said, this is a flow of carbon around the landscape. So carbon can also be lost via soil and plant respiration through those decomposition processes as well, and also lost via soil erosion. Now, with soil erosion, that's where we've got the physical removal of soil particles and the carbon that's associated with that particles as well. In terms of land management, there's a few pathways here that we can directly influence if we want to have strategies which are building soil organic carbon. We can influence the amount of plant growth through our grazing management and our ground cover management. So we can make sure that we've got more solar panels growing and photosynthesizing in our paddocks and capturing more carbon. We can influence carbon loss by making sure that we're retaining ground cover and protecting the soil surface. And we can also protect carbon once it's in the soil, again through surface soil protection and ground cover, and through processes and practices which enhance soil structure. Now, the flow of carbon, which we saw in the previous slide, is happening in this landscape here, in this cropping landscape where we've got cover crops. It's happening in this landscape here where we've got some early interventions and water management occurring. And it's happening here in this Mitchell grass paddock. Now, what's different is the size of the arrows or the flows of that diagram. So carbon is cycling on your paddocks no matter what's happening, but you can influence the amount of carbon going in and the amount of carbon that's leaving those paddocks. Now, I've used two terms interchangeably here. I've referred to soil organic matter and soil organic carbon. Soil organic matter is defined as the less than 2 millimeter organic matter fraction in the soil. Now, the reason we refer to it as less than 2 millimeters, and that's what we standardize in our labs, is because it's the form of organic matter that's most related to soil properties and soil functions. It's also a very efficient way of standardizing processes across different laboratories. It's composed of microbes, humus, and charcoal, like I spoke about in the previous slides. However, we know that organic matter in soil exists in all different forms and fractions and sizes. So we can have organic matter that is 2 millimeters, we can have organic matter that's 2 meters long in terms of plant roots and fungal hyphae. Carbon, on the other hand, is what we actually measure. So soil organic matter is made up of 58% carbon and 42% other nutrients. And those other nutrients are really important for productivity. So for example, nitrogen, phosphorus, and sulfur. The way that we measure carbon in soil is typically through the dry combustion method, and that gives us the soil organic carbon percentage. Now that's the total organic carbon in the soil. That includes the humus, the charcoal, and the particulate organic matter. So it's the total pool. Sometimes it's referred to as a percentage on your soil test results, and other times it might be reported as grams of carbon per 100 grams of soil. We also talk about soil organic carbon stocks. Now these are measured typically in tonnes of carbon per hectare and are reported to 30 centimetres because that's the international protocols. How we calculate soil organic carbon stocks are we use the carbon concentration, so the soil organic carbon percentage or the grams of carbon per 100 grams of soil. We use the depth of soil over which that sample was collected, and we use the bulk density of soil. Now bulk density is the mass of soil for a given volume. So we've got a concentration, a depth, and a mass of soil for a given volume, and that can give us the tonnes of carbon per hectare. The other unit, which often gets used, is carbon dioxide equivalents. Now this is used in carbon reporting. 1 tonne of soil carbon is equivalent to 3.66 tonnes of carbon dioxide in the atmosphere. If we just run through one quick example here, we can look at if we had a soil which had 0.7% carbon or 0.7 grams per 100 grams of carbon in the top 10 centimetres with a bulk density of 1.4, we multiply 0.7 times 10 times 1.4, which gives us 9.81 tonnes of carbon per hectare in the top 10 centimetres. If we were looking at that to 30 centimetres, we can still sample in 10 centimetre increments and still go through that same calculation, and what we do at the end is we add together each of those different layers to give us the tonnes of carbon to 30 centimetres. So in this example here, we had 4.48 tonnes in the top 10 centimetres, we had 2.82 tonnes in the 10 to 20 centimetres, then we had 1.32 tonnes in the 20 to 30 centimetres. We sum those together and we get 8.62 tonnes of carbon per hectare. So why are we interested in soil organic carbon? Soil organic carbon provides multiple functions within our soil. It provides cation exchange capacity. Now, cation exchange capacity is an indicator of inherent soil fertility. It's calculated as the sum of all the cations, the calcium, magnesium, sodium, aluminium, calcium, magnesium, potassium, sodium, aluminium in the soil. So we sum those together, we get our cation exchange capacity. Now, it's influenced by two main things: the amount of clay, because clays are typically negatively charged. Different minerals of clay are more strongly negatively charged than others, but the amount of clay determines our cation exchange capacity, and the amount of soil organic carbon also determines our cation exchange capacity. So if we've got a system which is building soil organic carbon, we're actually building the cation exchange capacity of the soil. We're building the soil's ability to hold on to and exchange those important nutrients. If we decline soil organic carbon, we're reducing the soil's ability to hold on to and exchange nutrients. Now, soil carbon is also really important for soil structure. A soil that is well structured has pathways for plant roots and soil microorganisms to move through. It has oxygen in the soil so that the plant roots and microbes can respire and breathe, and it also has an ability to be like a sponge and hold on to water. So we know that a 1% increase in soil organic carbon can increase our water holding capacity by up to 30%. Enhancing soil structure increases the soil's ability to infiltrate and be rain ready. So we're increasing the size of the sponge for both water and oxygen, but also for nutrients as well. Now, the more sandier the soil, the greater the impact of increasing soil organic carbon on these functions. But regardless of the soil type, all soils rely on soil organic matter for the provision of nutrients as well as the energy for biological processes. So 1% increase in soil organic carbon supplies an extra ton of nitrogen to the soil, over 200 kilos of phosphorus and over 160 kilos of sulfur. Organic matter provides habitat for soil microorganisms and energy for biological processes. So it's absolutely essential for soil function. Now, it's also important to remember that soils vary in their capacity to sequester and protect carbon. When we see that soil organic carbon percentage on our soil test results, it's dependent on a couple of things. First of all, if we go back to that flows of carbon diagram, it's dependent on the organic matter supply, so either the biomass that's grown on site or biomass that's brought to the site in the form of compost, and the balance of that with carbon loss, so carbon loss via decomposition and erosion. Now, this can be modified by the type of organic matter that's grown. So some plants are just more tastier to microbes and more readily decomposed than others. And also the soil's capacity to store soil organic carbon. And that can be determined by the amount of clay, the type of clay or the mineralogy of clay, the depth of soil and soil structure. Because remember, soil structure can protect soil organic matter as well. Now, these are the same factors that drive productivity, and some of these factors can be changed. So we can change the type of organic matter or we can influence that. And some can't easily be changed. For example, the type and amount of clay. In terms of our land management, we know that grazing management can influence the amount of biomass that's generated on farm. So we can graze so that we're keeping plants in an actively growing state. What does that do? That captures more sunlight and it puts more carbon into the soil through plant root growth and through that root exudation. In terms of data, we know that doing this can increase our soil organic carbon sequestration by up to 1 tonne per hectare per year. Now, it's important to note when we talk about these figures that soil organic carbon increases aren't linear. So generally when we average it over, say, 10 years, most of the increase when you have a practice change occurs within the first 5 years. They're highly dependent on seasons, particularly in rangelands environments. So it depends on effective rainfall. And it also depends on our starting level, soil organic carbon. So the lower the level that you're starting with, the bigger the increase or the more saturated the soil that can become. And also on soil type. Again, some of our soils are more responsive to practices than others. But replicated trials and published data shows that it is possible to build soil organic carbon through grazing management. So by increasing biomass supply, but also by grazing management, which influences the plant composition. So we can have the type of organic matter going back into the soil that's more readily stabilized and created into that humic form. And also ground cover protection as well. So we're avoiding the loss of soil organic carbon. Another example in this table here is water ponding in New South Wales, where what we've done is we've created an environment which can capture nutrients and moisture so that more photosynthesis can happen and more organic matter accumulation can occur. If we look further afield in America, there's been lots of studies which have, again, looked at the role of grazing management in rangeland systems to accumulate soil organic carbon, as well as the provision of nutrients such as nitrogen. Because remember when I said soil organic matter is 58% carbon, but it's a whole heap of other nutrients too. And microscopic livestock, so our soil microbes, also need nutrients to function. Through looking at grazing good country and poorer country by looking at our starting level of soil organic carbon. So we know that lower soil organic carbon starting levels are more responsive to some of these practices as well. So what these tables show us is that we've got carbon sequestration rates, which might range from say 0.1 tonnes per hectare up to 1.5 tonnes per hectare across that 30 centimetre interval. Now this is what the published literature is showing. It's going to be dependent on your own farm context, your soil type, your climate, but it just shows that strategies can be implemented to build soil organic carbon. But in some systems we don't see an increase in soil organic carbon despite best managements, and it's important to understand some of those reasons. Now, one reason might be background levels of soil organic carbon. So if you already have quite a high level for your soil type and environment, so a high background soil organic carbon, you might not detect that change in carbon sequestration. It might be occurring, but it might be undetectable. And the way I think about this is if we have two buckets that are exactly the same size. And one bucket is full of sand and the other bucket is completely empty. Now, if we look into the empty bucket, we can see that there's nothing there. If we take 1 cup of sand and pour it into the empty bucket, then look in, you can see that there's some sand that's been added to that empty bucket. However, if I poured that 1 cup of sand, exactly the same amount, into a bucket that's already full of sand, when you look in that bucket, you probably can't tell the difference. So it was an undetectable change, despite the rate of sand addition being exactly the same. We also have highly variable soils, and that spatial variability can make it really challenging to detect change over time, particularly over short time frames. As I've said earlier, soil type and climate are major drivers of productivity, and some types of organic matter accumulation, particularly in that particulate organic matter fraction, can be quite sensitive to management, but also sensitive to soil moisture conditions. Plant nutrition can be a major factor in determining whether or not organic matter can build up in the soil, or if the plants are limited in their ability to, photosynthesize as well through a plant nutritional deficiency. And also drought. As I said, the seasonal impacts of soil organic matter flows are very important. So it can limit the amount of photosynthesis that's happening. It can also influence the decomposition process as well. And in some cases, soil organic carbon just might not be a sensitive enough measure of that management change. But it doesn't mean that it's not an important measure to take notice of. So absolutely, there are multiple strategies to build soil organic carbon in rangeland grazing systems. Without a doubt, grazing management is king. So making sure that we're grazing so that plants are in that actively growing state. Making sure that we've got planned rest periods so that pastures can recover. Ensuring that we've got maximum ground cover to protect the soil surface and buffer the soil surface against those extreme changes in soil temperature and moisture. Including legumes or managing for legumes in these systems as well to get that nitrogen provision for our pastures and for our microscopic livestock. Nutrient cycling is really important, both for building humus, but also for ensuring those essential functions of soil organic matter. Landscape rehydration, so water ponding, spreading and pitting, can be an important engineering function to capture water and retain nutrients and moisture so that you can promote photosynthesis and carbon building in situ. Changing practice on degraded soils, so land use change, can be an important factor which really gets maximum sequestration in the early years. So going from a degraded crop to a perennial pasture, that can be an effective way of building soil organic carbon. And also adding carbon-rich materials such as composts and manures. Now these next factors are in green because they're an emerging and very exciting body of innovation and data that's coming online now, and that's in terms of mixed species plantings, so having that biodiversity in the pasture composition, biostimulants and microbes that store stable carbon. So using our fungi to actually not only capture nutrients and water for our plants, but making sure that they're creating stable carbon minerals in the soil, which can accumulate and be present for long periods of time. I often get asked about the interactions between soil microorganisms and grazing management. Wherever you are in the world, there are billions of organisms within the soil, all performing different functions. Now, this suite of organisms are quite different. The communities are different if you're in the rangelands environment compared to higher rainfall environments, for example. But their essential requirements are all the same. They like actively growing plants. So we've got plants that are pumping root exudates into the soil to support diverse microorganisms. Generally, they favour perennial-based systems compared to annual systems, and that's around that energy supply, year-round growth, surface soil protection. Legumes are really important. First of all, because of that symbiotic relationship between legumes and nitrogen-fixing bacteria. Also because legumes have a higher nitrogen content, which microorganisms like when they're decomposing and forming humus in the soil. So if you're managing for productive plants and maintaining ground cover, so plant and litter cover and minimizing bare ground, you can encourage and enhance the support of microscopic livestock. The role of grazing management is really important for regulating soil temperature, and we know that soil temperature and soil moisture are key drivers of microbial activity. Ground cover in particular influences soil temperature. Think about it as an insulator at the soil surface where most of that interaction between hot temperatures and management impacts occur with the soil, that interface. The more plants you have, the less bare ground you have, the more habitat, air, moisture and nutrients that you can have for those microbial processes. If we look at this, these dot points here, we can see at around about 18 to 24 degrees Celsius, we've got optimum soil moisture conditions for both plant growth and microbial growth. As soil temperature increases, soil microbial functions decrease. Moisture becomes limiting, and then temperature overrides their activity. Now, as I said at the beginning of the slide though, different organisms are suited to different environments. But generally, if we're managing for ground cover and perennial species, we're insulating the soil surface and maximizing microbial activities. So to end, carbon cycling on your farm already. To change it and to sequester more, you may need to change practice. So you need to think about what's your biggest lever. What's the biggest influence you can have on organic matter supply to the soil, organic matter protection within the soil, and maintaining ground cover so that you can minimize carbon loss. There may be some soil and climate factors that limit carbon sequestration. Soil factors may be different in different parts of your property, and it's really important to get to know your soil types and understand the higher sequestration potential sites and the lower sequestration potential sites. The benefits of soil organic matter to soil fertility and structure come from carbon cycling. So organic matter needs to be mineralized and cycled through our microscopic livestock, our soil microorganisms, so that it can provide nutrients for plants, so that it can enhance soil structure by fungal hyphae enmeshing soil aggregates, or bacteria producing polysaccharides which stick soil particles together and enhance structural stability of the soil. To increase soil organic matter on your farm, you need to consider for your own canvas, for your own property, what's the right practice in the right place at the right time, and that can maximize your opportunities to build soil organic carbon